Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
Last week, we used GLMakie to create dynamic plots that contain interactive sliders, buttons, and menus. Today, we're going to return to GLMakie to learn how to animate data. By the end of this tutorial, you will know the fundamentals of animation and how to create and save your own animated mini-movies. You'll also learn about Monte Carlo Simulations and how to scale up your animations to handle large datasets by animating a famous Monte Carlo simulation example. This should be another action-packed episode, so let's get started. Open VS Code and maximize the terminal panel. Start the REPL by holding down the Alt key and then hitting J, then O. Make a new directory called tutorial02/11 by using the make directory function. Change your present working directory to your new directory by using the change directory function. Enter the package REPL by hitting the closing bracket. Activate your new directory by typing in activate space period, and then hit enter. Add the following packages and versions. Type in status to confirm that the correct packages and versions have been added. Exit the package REPL by hitting backspace. Minimize the REPL. Create a new file by going to File, New File. Save the file as tutorial02/11.jl by going to File, Save As. Be sure to save your file in your new directory. I'm going to be adding a header to my file, but there's no need for you to type this in. You can access the source code for this tutorial in my GitHub Repository. The link is in the description below. Animation is an optical illusion. It tricks the human eye and brain into believing that an object is in motion, when in reality, there's no movement at all. In this simple animation, I appear to be moving across the screen. In reality, this animation was created using 24 still images called frames that were displayed on your screen at 24 frames per second to generate a 1-second video clip. In fact, this entire YouTube video is made up of frames containing still images that are being displayed at 24 frames per second. 24 frames per second is called the frame rate. It's often referred to as frames per second or FPS. Frame rates can be a confusing topic because there are so many different frame rates in use today. For film and television, the standard frame rate in the US is 24 frames per second, but in Europe, the standard is 25 frames per second. Videos captured on your smartphone may be at 30 frames per second or 60 frames per second. Some common frame rates for YouTube videos are 24, 25, 30, 48, 50, or 60 frames per second. In order to capture slow motion video, a digital camera may be using 120 frames per second or even 240 frames per second. This may lead you to wonder if a higher frame rate means a higher quality. The answer is, it depends on the application. According to this Wikipedia article, the human vision system can only process 10 to 12 images per second and still perceive them individually. The old school cartoon animators knew this, so they produced hand-drawn animated cartoons at 12 frames per second. Hollywood movies were historically shot at 24 frames per second and also displayed in movie theaters at 24 frames per second. Since animation is a resource-intensive endeavor, every effort is made to use as few frames as possible, and 12 frames per second is sufficient to give the illusion of movement. Higher frame rates do allow for more fluid motion, but at a cost. Frame rates lower than 10 to 12 frames per second are cheaper, but to the human eye, they appear choppy. With the advent of computer-generated imagery, or CGI, one would think that all of the old rules can be thrown out. But the reality is that despite advancements in technology, the human eye and brain have not evolved. So we're still adhering to the traditional techniques of creating still frame animation and then playing them back at a certain frame rate to trick our eyes and brain into believing that objects are in motion on our digital screens. The biggest difference is that we can now use our computer, along with a programming language, to automate a lot of the work that used to be done manually. While there are many technical aspects to animation, at its core, animation is not about the technology. Rather, it's about storytelling. It's a way to provide an abstraction of a complex world in a simplified, easy-to-consume format, in a way that connects with your audience emotionally. Now that would be a useful skill to add to your toolkit, right? Let's take a look at an example of how we can create an animated plot using GLMakie. In this example, we're going to create an animation showing the population growth for the world by region and by year. This data comes from Wikipedia. The population data from 1950 to 2015 are estimates from a UN datasheet in 2015, while the population data from 2020 to 2100 are estimates from the UN in 2019. In the interest of time, I have prepared a CSV file containing this data, which you can download from my GitHub repository. Go to github.com and search for julia4ta/tutorials. Click on the link to go to my repository. Click on the Series 02 folder. Click on the Files folder. Click on the population by year.csv file. This next tip comes from viewer The Grand Poobah, who shared it in the comments section of one of the other tutorials. Rather than left-clicking on the raw button, right-click on the raw button. From the menu, select Save Link As. Save the CSV file to your Tutorial 02x11 folder. Now that was much easier than copying and pasting the raw text. Thanks, The Grand Poobah. Now let's go to the editor and load this data into a data frame. Let's take a look at this data by using VS Code Display. The first column is the year in increments of 5 years, from 1950 to 2100. The rest of the columns contain the population data in millions of people, starting with the total world population, followed by the individual regions listed in alphabetical order. Our goal is to animate this data, showing how the population data changes over time for every region. Let's create a column vector containing the names of the separate regions. Now that we have our data, let's use GLMakie to set up a plot. I am recording this on a 4K monitor, and this resolution is for a 4K display. If you're on an HD monitor, you might want to use a resolution of 1920 by 1080 and reduce the font sizes accordingly. A separate display window should open up with a blank screen. The next step is to set up our axis. I split the title into 2 rows. When typing in the second row, make sure that you do not include a tab at the beginning of the line, since Makie will actually include that tab in the title. This title is just a hacky way to avoid adding a legend. This syntax is similar to other axis layouts that we've used in past tutorials. We're almost ready to start creating our animation. First, we need to do a little prep work. This is the iterator that will generate separate frames for our animation. In this case, we will end up with 31 individual still frames. These are the different colors that we will use for the different regions. You can pick any colors that you like. We are now ready to create our animation. In GLMakie, you create an animated plot by using the record function along with the do-end syntax. You can think of the do-end syntax as a for loop. It will iterate as many times as you tell it to. In this case, it will iterate 31 times, once for every frame. Makie supports several different video file formats. I'm using the MP4 file format because it's a commonly used video file format. All of my tutorials are uploaded to YouTube using the MP4 file format. I'm using a frame rate of 12 frames per second for the reasons discussed earlier. Doing some simple math, 31 frames at 12 frames per second will create a 2 to 3 second video clip. Conceptually, the workflow is similar to the old school animation technique of creating one frame and then taking a photo of it, and then creating the next frame and then taking a photo of it, and so on until you've created and photographed all of your still frames. Next, you gather all of your still frame photographs and splice them into one continuous roll of film, which you can then play back on a projector. But rather than doing this manually, Makie will do all the work for you. Let's run this code to see what it looks like, and then come back to this code after we watch the animation. Go to your project folder and open up the MP4 file. It's a short clip, so I'm playing it in a loop. So, what does this show us? It looks like the world population is projected to level off at some point in the future at around the 10 to 11 billion people range. It shows a population rise and fall in Asia. It shows a continued dramatic rise in population in Africa. It shows a gradual decline in the population in Europe. Finally, it shows stability in the populations in the Americas and Oceania. You can see all of that in the static plot. But which one is your eye drawn to? Which one tells a better story to your audience? Now, let's go back to the code and talk about it. While this animation may be interesting, there are a number of issues with the code that I wrote for it. First of all, this animation is too short. A 2 to 3 second clip is not long enough to tell a compelling story. As a result, I had to keep looping it, which can get annoying for your viewers. For your own animations, you should consider animations that are at least 10 seconds long or longer. 10 seconds at 12 frames per second means that you should have at least 120 individual frames, not just 31 like I had. Second, the code is not very efficient, so it's not scalable. You may not be able to tell in this short animation, but using this code would not work with a large dataset. I'm basically replotting the entire dataset for every frame. What I should be doing is just adding to the existing plot with new data only. This is a case of do as I say and not as I do. In the next example, I will show you a much more efficient code that will allow you to animate very large datasets. But before we get to the code, we need to discuss Monte Carlo simulation. Monte Carlo simulation, or the Monte Carlo method, is a way of estimating the possible outcome of an uncertain event by using random numbers. This may sound absurd, but it turns out that using random numbers is often a better way to model the real world than using discrete formulae. While the concept can be traced back to the 18th century, the modern application of the Monte Carlo simulation emerged during World War II in the 1940s. Stanislaw Ulam and John von Neumann, yes, that John von Neumann of the von Neumann architecture, are credited with inventing the modern version of the Monte Carlo simulation while working on nuclear weapons research for the United States. Ulam is credited with inventing the algorithm, while von Neumann is credited with programming it using early computers. Due to the secret nature of their work, they gave it the code name Monte Carlo, named after the famous casino in Monaco. While the Monte Carlo simulation has many different practical applications, we're going to focus on a famous example of using the Monte Carlo simulation to estimate the value of pi. There are several videos on YouTube that show this, so I'm certainly not the first one to upload a video on this subject, and I suspect that I will not be the last because it's such a fascinating case. Here's how the thought experiment goes. Start with a unit circle and inscribe it in a square. Since the radius of a unit circle is 1, we know that the length of each side of the square is 2. The area of the circle is pi times the radius squared, or pi r squared. Since the radius is 1, the area of the circle is just pi. The area of the square is just 2 times 2, or 4. So, the ratio of the area of the circle to the area of the square is pi divided by 4. In order to estimate the value of pi, we can generate random numbers and plot them in the square. This is sometimes likened to throwing darts onto a dartboard. When finished throwing darts at the dartboard, all we need to do is count the number of darts within the circle and divide it by the total number of darts. In theory, this ratio should be equal to pi divided by 4. Therefore, the estimated value of pi is 4 times the number of darts within the circle divided by the total number of darts. If this is your first time hearing of this, you may be thinking that this is just ridiculous. How could you possibly come up with a number as specific as pi just by using some random numbers? This is really the essence of the Monte Carlo simulation. The idea is to use random numbers to estimate something specific that may otherwise be too complicated to model. The Wikipedia article includes an animated GIF that illustrates how to use the Monte Carlo simulation to estimate the value of pi by plotting random points onto a quarter unit circle. Let's use GLMakie to create a more sophisticated animation of this Monte Carlo simulation in 4K and saved as an MP4 file. As with any plot in Makie, start by initializing the plot. Now, add an axis for our dartboard. This is our 2x2 square that we will use as our dartboard. Let's add a second axis which will keep track of our estimate of pi with each dart throw. Let's fine-tune our layout to give it a little more room on the right-hand side. Finally, let's add a horizontal line showing the value of pi. That does it for our layout. Now, let's generate some random data. I'm going to use a random seed, so you should be able to reproduce my dataset. Next, we need to select how many darts we want to throw. This number is really up to you. The lower the number, the less accurate your estimate will be. The higher the number, the more accurate your estimate will be, but it will take more processing power to create your animation. I'm going to use 144,000 darts. You'll see in a moment why I chose this number, but you can choose any number. Next, we need to generate random numbers for the x-axis and for the y-axis. Because our dartboard goes from -1 to +1, we also need to include a random -1 or a random +1 to multiply to our random number. You can see that it's just some random floating point numbers between -1 and 1. Same thing with y. Next, we need to determine if each xy pair falls inside the unit circle. We can determine this by using the Pythagorean theorem to see if x squared plus y squared is less than or equal to 1. This creates a column vector of booleans, which are just ones and zeros. We also need a running cumulative total of the number of darts inside the circle. We can do that by starting with an empty array and then pushing that information into the array using a for loop. You can see this vector is just keeping track of how many darts have landed inside the circle. To be safe, let's double check our code. If we did everything right, the last value of the circle sum vector should be equal to the sum of the circle vector. So far, so good. Finally, we need to calculate our estimate for pi at each dart throw. As you can see, the first few estimates are not even close. But as the number of darts grow, the estimate begins to converge on 3.14, but still varies along the way. Let's take a look at the final estimate. So, this Monte Carlo simulation is estimating that the value of pi is 3.140361 repeating, which is close, but not exact. Pi is closer to 3.14159. Let's see how far off we are in terms of percentage. So, we're off by 0.04%, which isn't too far off considering that it was determined by a bunch of random numbers. Now, let's see what all of this data looks like in an animation. Unlike generating static plots, recording animations takes some pre-planning. For our animation, let's select a different color if the dart falls within the circle. You can select any colors you like. I'm going to use green for darts that fall inside the circle and red for darts that fall outside the circle. As you can see, it's just a column vector containing the colors for the darts. We need a vector containing the numbers 1 to 144,000 to use in our plot. This next step is very important. We need to determine how many frames we want in our animation. While it may be tempting to plot one dart per frame to get 144,000 frames, this would be resource-intensive, inefficient, and not very practical. A more efficient way would be to plot clusters of darts per frame to reduce the number of frames. This will still allow us to tell our story while avoiding the creation of an unnecessarily large video file. When deciding on the number of frames, you work backwards. Start with how long you want your animation to be, and then multiply by your frame rate. That will give you the number of frames that you will need to create. In my case, I want a 30-second animation playing at 24 frames per second. 30 times 24 is 720. That means I need to create 720 frames for my 30-second animation. In order to get through all 144,000 darts in 720 frames, I will need to plot 200 darts per frame, since 144,000 divided by 720 is 200. And rather than replotting the entire plot each time, I'm just going to add the incremental dart throws for each frame. Let's take a look at what this animation looks like. Go to your project folder and play your animation. This animation really gives a sense of the randomness of it all. Subjectively speaking, the darts seem uniformly distributed and random. Early on, our estimate is not even close to the value of pi. As the number of darts grows, the estimate gets closer to pi, but it's still off. Even at the end, it's clear that there's still a lot of white space left on the dartboard, meaning there's still a lot of room for error when estimating the value of pi. While the static plot shows some of this information, it doesn't reveal the entire story. Seeing your data in motion often provides new insights that you may have otherwise missed. Fascinating, right? Before we go, be sure to hit Ctrl+S to save your file. Next, I'm going to share some tips to consider when creating your own animated masterpiece. This is not meant to be an exhaustive list, but here are some tips to consider when creating your animation. 1. Ask yourself, do I need an animation? Animation is a resource-intensive endeavor, so don't spend time creating an animation when a static plot will suffice. Good candidates for animated plots are large datasets that show differences at the beginning, middle, and end. 2. Focus on the story. Your animation should be about the story and not about the animation technology. Ask yourself, does my animation help me communicate my analysis, or is it just a fancy motion graphics spectacle? 3. Select a low frame rate. Use the lowest frame rate possible. A good starting point is in the 10 to 12 frames per second range. You can always go higher, but going lower will result in choppy animation. 4. Make sure you have enough data. Remember, you need at least 120 frames to make a 10-second animation at 12 frames per second. 5. Select a smaller scene resolution. Both of my examples were made for a 4K monitor, but in many cases, an HD resolution or smaller may be sufficient, and will result in a much smaller file size. 6. Add incrementally to existing plots. Don't try to replot everything for each new frame. Conserve resources by adding incrementally to existing plots. 7. Watch your own time. I'm guilty of violating this one. Remember that your own time is a resource too. It's easy to go down an animation rabbit hole only to discover that you've wasted hours working on an animation project. There's no point in spending hours creating a cool animation if you're just going to miss all of your other deadlines. And 8. Have fun. Looking at a static dataset can be pretty dull, but animating it can bring it to life. Tap into the creative side of your brain and have some fun. While I think that interactive plots are becoming more common, I think that animated plots are still somewhat exotic. Every time I see one, I find myself mesmerized by it. Now that you have a foundation in animation, you can bask in the knowledge that you possess a rare but powerful analytic tool that you can unleash when the time is right. Remember to always use your newfound power for good and never for evil. Well, that's it. Congratulations if you made it this far. Today, we learned how to use GLMakie to animate data. Being able to animate plots is a powerful tool that you can use in your own analysis to extract new insights. It also allows you to better communicate your analysis to your audience by giving you the power of storytelling. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. New tutorials are posted on Sundays/Mondays. If you have any questions, please post them in the comments below. Please feel free to share these videos, since these tutorials are getting rave reviews. Just listen to what the professional reviewers are saying.
It's disappointing, ladies and gentlemen, but hey, it's all random.